Okay, thanks. So yes, Malebolgia, structured concurrency for NIM is the name of my talk. NIM is a programming language. It's a systems programming language, and it's already 16 years old, so it predates Go and Rust. And some claim it should be a backronym for New Intended Modular 3, but I don't think that's really fair. Nevertheless, Modular 3 was a big inspiration for us. In Modular 3, there is a distinction made between untraced and traced pointers. So there is like garbage collected pointers and unsafe pointers, and this allows us, this gives us a very flexible language. However, other sources of inspiration have been C++ and Lisp. So back then the problem was the two, nowadays it's called the two language problem. I think the Julia developers came up with this term. But yeah, this is what we tried to solve. So we wanted a single programming language that gives you the convenience of a scripting language as well as the performance of native code so that you can optimize your hotspots in the very same language. It's right now used successfully for game development, compilers, scientific computing, and on embedded devices. And over the years, its runtime became so refined that we support hard real-time system. So there's a cost model attached to NIM so that you can reason about the performance in a somewhat abstract manner. And how we do that is basically these days a very, very optimized implementation of reference counting where it would elide these reference counting operations at compile time. And there's also annotations that you can use to even improve the optimizer's capabilities. Okay. Right now, the most famous project implemented in NIM is probably called Nimbus. It's an implementation of the Ethereum cryptocurrency by a company called Status, which is also sponsoring our work. So if somebody sees that, thank you. Okay, now let's have a look at a bit of code. So this is LambdaConf. So no hello world, but instead Fibonacci. Here we have this keyword proc, which is for procedure. There is also func for function. And the distinction is that in a function, you are not allowed to have side effects, but in a proc, you can have side effects. So this is purely functional. So I could have used the func keyword here, but I chose not to for reasons I will go into. And here, so this n is like an implicit return, right? If n is less than 2. Otherwise, we call itself recursively. So this is indentation-based syntax with a static type system. Very familiar syntax, I think. Close to F# these days, I suppose. Okay, and if you run this code, like Fibonacci of 40, on this oldish laptop, it takes less than 1 second. So now a couple of more words about NIM so that we can read the longer examples more easily. So in Lisp, there is only lots and lots of parentheses, like function application, or it could be a macro call. And in NIM, it's comparable, but NIM is not homo-iconic, but instead, many, many constructs are mapped to this idea of it's a function application. And now, don't get overwhelmed. This is very easy. These two lines here say you can leave out the parentheses for a function call. These lines here teach you that you can use the dot notation to emulate object-oriented programming. This one deals with string literals and how to make them easier to use for regular expressions, not important. And now here, this is important. So with the colon and then indentation, or you can pass a full block of code to this f. For example, I can create a macro called lock. Then I lock this x, like acquire the x. Then this whole block of code echo hi is passed to this lock macro. And in the implementation, it would then say hi, and then it would release the lock. There is one exception, like if you have a nullary function, you cannot leave out the parentheses so that f is available as a first-class citizen in the language. So if I say map of f, I actually pass the f itself to map and not call the f. Okay, so, and now one more slide for general NIM. And these two slides describe most of the language already. So after these slides, you will be familiar with most of NIM's concepts. Okay, so NIM is actually very strong at custom operators. And an operator is simply a function or a proc with a name in backticks. And here I use the func, so no side effects allowed. Yet I say var int, which means it's mutable. So I mutate the x, right? I add the y and the z values. The y defaults to 1. The z value defaults to 0. And there is no distinction, like this is a ternary operator, let's say, right? So I can call it with the backticks g with 3 arguments. But usually an operator you would call with a binary syntax here. So then it would use the default value for z, or as a unary operator, and then it would use both default values here. Okay, and this var int thing here is implemented behind the back as a pointer. And this will also be important, so remember. Okay, Malebolgia is a library for NIM that gives us a thread pool. And before Golang existed, usually it was called, the keyword was spawn. Spawn some task or spawn some microprocess. And it turns out that spawn is also a superhero, this one here. And in the comic book, the spawn, the hell spawn, was created by Malebolgia. So this is where the name comes from. So in the comic book, Malebolgia creates new hell spawns. And for us, this Malebolgia library gives us the spawn construct. Okay? And with a little bit, it's hard to see. So we turned this guy here actually into this iconized symbol to make it nicer to look at and to avoid some copyright problems. Okay, so thread pool for NIM, as I told you, there's the idea that the thread pool is always there, like it's stored in global storage, but you can wait for a task group independently of this thread pool. We detect at compile time read-write and write-write conflicts. We can do that because this is implemented as macros, and macros cannot just generate code, but also inspect code, right? We can analyze at compile time things that, like these conflicts. We'll see how that's done soon. We support cancellation and timeouts. And finally, this Malebolgia library is my third implementation. Like I tried to add in thread pool for NIM. The first implementation was, what's it called? Like, this purely functional, right? This, well, I'll come back to it. So the second implementation then was std thread pool, and we found many problems. So it's actually in the standard library, the second implementation, and then we figured out that we made it too complex. So there would be cases where people would write their program and tell us like, okay, this is fine, but look, I'm running into a deadlock here. So fix it, right? Your library is broken. And then you would be like, yeah, okay. Good luck, I mean. So implementation simplicity was a major goal for Malebolgia. And we achieved that, like it's less than 300 lines of NIM code. We also managed to add to have low energy consumption, and maybe the time will allow me to talk about that. And even though it's a very, very simple implementation, we actually managed to win benchmark with this. So Fibonacci that I've shown you is actually a standard benchmark for thread pools, as is DFS. And this DFS benchmark we do win against the competition. The competition in this case is called Weave. It's an alternative thread pool implementation for NIM. So you can imagine that there is some competition, right, among library authors who adds the best thread pool to NIM. And this crawler benchmark, I came up with it on my own because these benchmarks here are basically toys. And I tried to create a benchmark that is actually has more relevance for the real world. And it turned out that we do win this benchmark as well. So Fibonacci now concurrent or in parallel. We import this helper library, Malebolgia. We need to create a master object, and you can think of this, in Python land it's called the nursery. In Golang it's comparable to a weight group. But for us it's basically a capability. So if you have a master object, then you are allowed to say this spawn on this M, right? And you are allowed to wait for all tasks that are here grouped here. So, and this is also this the structured concurrency. So you know after the wait all call in line 11, you know that the concurrency is over, and that you are then able to read from A and B. And this arrow here is a special syntax. So Malebolgia adds a custom operator to NIM. So this means like create a task, fib of n-1, and eventually the result will be available in this A, and A here is a variable of type int. Likewise for B. Okay, now, and then you have parallelized it successfully, right? It's recursive, so it would use all of your CPU cores, and when you then run this, it takes not 1 second, but 10 seconds. So it's 10 times slower. And now you can say, yeah, look, this is what you get for focusing on implementation simplicity. It sucks. So you can compare it to the Weave implementation, which uses work stealing and all the crazy advanced algorithms. So you can port this code to Weave, and it would run in 4 seconds. So still 4 times slower. So the problem is, in all of these implementations, that, okay, you don't create a thread here, but you need to create a task, send it to the queue, and have the worker threads pick up the tasks and run it. And this task creation step here can easily be more expensive than the simple function call. So what you then can do is you combine the ideas, all right? So here now I have fibs, not fib. So the sequential version, right? Again, simple recursion. And my fib implementation simply says, yeah, fibs, okay? So basically, I now use only 2 cores, right? And then you can run this code and see that it would take half a second. So now, finally, you get some speed up. Now, a little bit back to this. So, as I said, my implementation, 10 seconds. The good implementation, 4 seconds. The linear version, 1 second. So now you can think about an alternative Malebolgia implementation that does the following. Create masker, yeah, ignore. I'm not going to do anything. Await all, yeah, I don't care. Spawn fib n-1 to A. I say instead, yeah, I just run fib directly, store it to A. Likewise for fib, so that I get the sequential version back again. I would take 1 second. I would win the benchmark. And I would have a thread pool implementation winning this standard benchmark that doesn't use any threads, right? And this, this is terrible. And this is not specific to this Fibonacci benchmark, but also to this DFS benchmark, as we'll see. So that's why I tried to come up with a benchmark that makes more sense. All right. Now let's have a little bit of I/O. So now hello world, but with Malebolgia. So I have this helper proc here, and now it really needs to be a proc because it's a side effect, right? Calling hello. So hello for the ith time, and then I'm going to call this greet of I 5 times. And finally, okay, I know after line 9, the concurrency is over again. So structured concurrency means that you know precisely in the source code, you can see it where the control flow converges back again. Okay, so when you run this, this might be a possible output, and the point is it's not deterministic. We don't try to prevent you from doing stuff this way. And as I said, like thread pool was my second implementation, and this one also offered a spawn keyword, but here was the idea that, and this, now read this please as has the type of t. So if f, a, b, c has the type of t, then spawn of this construct has the type flowvar of t. This is a data flow variable, or sometimes called a future. And by design, you cannot have data races with this idea of a flowvar because you can only store once a value in it, and then you can read from it as often as you want to, but it would block. So if the value is not yet available, the read operation, this time called roof of x. So again, libraries sometimes love to introduce new operators. So it would block until this is available. And then, so data races are impossible with this design. So here I have an example using this std thread pool. The task is to compute the most commonly used word across these 4 data files. And since, I'm not showing it here, so this count words of f returns type count table ref of string. And since this returns t, spawn of this returns flowvar of t. Okay, and then after I created these tasks, I can wait with this roof, right, this read my flowvar operator, merge the results back and get some result. Now, the problem here is that I can easily make a mistake, right? I could say spawn, like I could even say roof of spawn of count words of f. The type system would be happy, right? So it wraps it in a count table ref. The roof unwraps it immediately, and then I would lose all parallelism in this example because I wait for the results too early before I schedule the other tasks. There's also, alternatively, you could also say, yes, look, I wait for all the tasks, similar to await all with the sync keyword. And here now we can see the downside of the older idea is that you wait with the sync for all spawned tasks, but it might not be the case that you actually know what tasks are running in your thread pool because the thread pool is like shared, and maybe you have a more complex program than this one. Okay, rewriting this too. Let's look at this. Okay. So rewriting this program to use this new Malebolgia library. The flowvar of t is gone here, and like the assignment is now spelled with this arrow operator. And the reason why we use this new syntax here is because this await all macro actually tracks these expressions and prevents us from introducing read-write and write-write conflicts at compile time. So there's some special checking going on, so that's why we also introduced some special syntax for this. And here then the roof is gone. So this was also a pet peeve of mine. These flowvars of t's, they are usually annoying to work with because you only care about the t. And if you compare this to programming a GPU, for instance, you have a matrix of floating point values. You don't have a matrix of futures of floating point values, right? Because it's just too annoying to work with. Okay, so Malebolgia works well on embedded devices. We use bounded memory consumption because we really try to target embedded devices. So the idea here is we use a single array of fixed size for threads, but it's configurable at compile time. And the task queue, we use a single task queue, so there's this high contention on this thing, but nevertheless, it works out for us. This task queue is also bounded in size. And now, if you think about this, when you have fixed size things, actually it does solve the back pressure problem as a side effect. So in concurrent systems, the back pressure problem is somewhat like you have a producer and it produces tasks too quickly, so the consumers cannot keep up with the work, and you would run out of memory, for instance. Or you can construct cases where it actually produces a service attack, and so this is a very nasty problem. And now you can say, yeah, but this is like the most terrible solution you can imagine to solve this problem, but but it is a solution. So yes, the static scheduling here is not really a goal, but it's my ideal. So ideally, I would love to have static scheduling. However, we use like the POSIX create thread APIs, which do not offer the control that we would love to have here. So the idea is, ideally, you specify the scheduling behavior at compile time, so that you know, like you run then the program a couple of times, and you know in production the system will behave the same way, right? Because you eliminated the dynamism here for the scheduling. Okay, we've already seen that. So more benefits of the structured concurrency idea. It turns out it works very well with low-level memory management. So in NIM, we compiled to native code. And the function call stack is implemented as it is in C or C++ or Rust, which means that it can happen that you take the pointer, like you have an activation frame in memory, you take a pointer to this, and then the activation frame disappears because it's a stack, and then you read from this pointer and get undefined behavior and all sorts of bad things. But thanks to this structured here, this await all, you can actually send pointer values to the different thread and be sure that the value lives long enough. Another benefit is that it works well with exception handling. So imagine you create 40 tasks, one of them fails. What are you going to do? Like, after the await all construct, the concurrency is over, so then you can re-raise the exception. And that's exactly what Malebolgia does. So it remembers the exception for you and then re-raises it when it's clear that this can work. Here I have an example for cancellation. Okay, so we create this master again. Then we wait for all tasks to finish, and while it's not canceled, the user can enter some string and send it in. And the input can either be start or stop. If it's start, we create a new worker task, and we pass this master handle here, not the master, because the idea is that you cannot copy these master capabilities, but you can allow access to this underlying thing via this master handle. All right, and this worker task here is easily triggered, right? It's some snowflake. Unless it's canceled, it says I'm triggered, I'm really angry. Then it waits for 3 seconds, and then it would say triggered again, unless the user types in stop. Okay. Now, here is a new thing, active producer equals true, which is some way to influence the scheduling. So usually what could happen here is that Malebolgia looks, is there a worker thread ready for this task? And if not, it would run this function here directly on the main thread, which is usually great for performance. But in this case, it would mean that the main thread would go into this sleep cycle here, preventing the user from entering data. And this is what this flag here does. It basically says, spawn, please really run it somewhere else, not on this thread that called into the spawn. Okay, let's see where we are. All right. Okay. We had an example with this var_t parameters, like mutable parameters in NIM. And we have already seen that you can actually take the address of a stack variable and pass it to this thread pool. However, Span does not support these var_t parameters for the reason that we thought, if you mutate things this way, it's likely that you mutate the same location, and you would need protection via a lock. So that's what Malebolgia instead offers. But I mean, we could do that. We decided not to. Okay. This is, yeah, visible. All right. So again, we want to count words. This time, no return value here. Instead, we mutate in place this count table, and it's PTR and uses address of. And especially address of is a keyword in NIM, and that screams for a NIM programmer, this screams unsafe. So this is now going into low-level unsafe territory. However, we know, thanks to this await all, that it's actually safe. It's just, we know it's safe, the compiler unfortunately doesn't. And then this is pointer dereference syntax here. So you can only access results when you have the lock. Okay, so if I have a lock, and this is a ticket lock, so Malebolgia also implements its own locking data types because these are then optimized for embedded devices. So these use atomic instructions under the hood. Okay, so this address of here is kind of ugly, but what's worse is that now this lock here, it protects the results, but that's not visible in the source code, right? These are just two separate parameters. So what we would like to do is we would like to combine these so that the type system can ensure that I access results, that it's not possible to access these results without having the lock. Okay. Yeah. So this is then the lockers type. Now this count table is protected by this locker of T. And you need to unwrap or unpack this thing. So you say, yes, lock this one, right? And this SR means results has the type locker of count table of string, and the R has the type count table of string then. So, and then this is the strange verb for count the word. It's just called inc in NIM for historical reasons. And okay, and now when you create this thing, you need to kind of nest these things together, right? So you need a locker and a count table so that the locker understands what it needs to protect. And here now the address of operations are gone. So this is now very readable code. And finally, there is like lock SR, and there is also unprotected SR, because again, structured concurrency, we know after this await all, like we can access these results again because we are the only one left who can access results. But the type system doesn't know that, so we need to say, we need to unwrap this anyway, but this unprotected doesn't acquire any lock. And now you can imagine some tool support where it would check statically that you use this unprotected construct only if you are not in an await all construct. But we don't do that. We could. Okay, now this other benchmark, depth first search, I think it is. But to be honest, I don't really know what it does. It just computes a sum of values in some crazy way. But that's not important. So again, here, since our DFS actually returns something, our spawn needs to store the end result somewhere, and in this time we store it in sums at position I, right? And here, we actually win this benchmark because we can say here it's just a sequence of int and not a sequence of flow vars of int. So this object creation step for flow vars doesn't have to be done, and that's how we win this benchmark. Okay, now I've already hinted at that we actually detect some problems at compile time. Okay, so this is my completely incompetent attempt to unroll this loop 2 times. All right, and I got it completely wrong, but the point is, now 2 DFS tasks compete for this resulting location where to store the result. So this is a write-write conflict. And this await all, as I said, tracks the expressions that are part of this arrow. And it would tell us at compile time there's a conflict here. All right. Okay. This is Turing Prize-worthy stuff, right? So, but how smart is it? Let's try to trick it. Same program, same bug, but now I introduce some alias, so J is the same as I. It's the same bug. The question is, does it still detect this bug? And the question is no. It does not. It doesn't even try. Worse is better. So the STD thread pool implementation actually had it actually had a proof engine and a calculus trying to prove that all these array slices involved are provably disjoint, right? Because when they are disjoint, it's okay. The problem was these things can have bugs. But worse, you also need to provide good error messages then. And you need to distinguish everywhere clearly between I can prove this is a bug, and maybe it's correct, but I can't prove it correct, so you need to rewrite the code. And then ideally, your error messages indicate how to rewrite the code to make it compile. And this was just too much work. And also, our users said, okay, while you try to figure this out, just give me some way to just be able to write my more complex code. So to think, you should think about this as a typo checker, right? We try to prevent some simple typos at compile time, and then we tell you, use Valgrind or the thread sanitizers for more complex scenarios. Okay, and now we can, with this await all construct, we can actually implement some higher level functionality. This is also like Malebolgia. 1 second. Oh, I'm quick. All right. So Malebolgia offers these par map, so the map operation, functional programming, but in parallel. Apply is the same one, but this one says, I take an array and give you a new array. This one says, I take the array and mutate it in place. And reduce is reduce, and find is find. So Malebolgia offers these algorithms for you, but I'm going to show you how they are implemented because that's very elegant. So apply, close enough. So apply, this is the signature. Apply is actually a template, which is a simple form of macro. It mutates the incoming array. The bulk size I will go into. And the operation I left untyped, but I could be more specific. So OP is like a function that takes this T and mutates this T because the idea is to apply OP on every element of this data in parallel. And the bulk size is again tied to our cost model because it can be the case that your task is actually too quick. So the task creation step would again be too much overhead, so you wouldn't get any performance benefit. Okay, so as an example, I create a sequence of numbers from 0 to 10,000. I have some helper function here. I could also write a lambda, but never mind. So this helper function mutates the int directly. So in-place mutation here, right? X times 4. And then I say apply this multiplication of 4 on my test data. And the 600 here is this bulk size. Okay, because multiplying by 4 is so cheap that you want to split your input data into big chunks and then send the full chunk to the thread pool and not a single array element. And now you can also reason about the code again. For example, let's say I have 4 cores on my machine. I have 10,000 elements. The ideal bulk size for me would then be 10,000 divided by 4. So a better value than 600 would be 2,500. And then you could run this on this machine and see if like this value 2,500, just a parameter for performance tuning, if this value would be the best value for your program. And you would see that indeed it is. But it could be that in this Malebolgia thread pool, there are other threads already busy while you try to do this. So you don't want to, like you need a smaller step size or something like that. So you need to benchmark and see what values work for you. Okay, and this is the implementation. 15 lines of code. This is the complete implementation of this parapply here. I only throw away the documentation comment. Okay? So what does it do? Well, we split up this bulk size. We do some array address arithmetic here. So again, we love custom operators sometimes. Okay, so here I have this add bang operator, which is basically in C it would be pointer plus I, right? But in NIM it doesn't do pointer arithmetic, so instead I take the address of data at I. And there's a further complication here because NIM has this idea of an array slice. It's called open array, but NIM tries to be memory safe, and it doesn't understand that this way is safe to do, okay? So I actually had to implement my own array slice. This is pointer to unchecked array to work around this. But since this is the high level implementation and like the high level interface, and in the implementation I should be allowed to use unsafe code, right? Okay. Yeah, and it can happen that the length is not divisible by your bulk size, so you need to one final step here for the rest of the data. And the worker here is this one, like it does sequentially this OP of A at position I. Okay, but the point is 15 lines of code, production code with this setup. All right, more time. Okay. Yeah, now we go through this example. Parmap again. Can I get it? Yeah. Like apply, but why is this still? This is a typo. So forget about this var. The idea is it takes this open array and produces a different array. Okay, let's have a look at it. So now no in-place mutation here, right? I get an int, I return an int, x times 4. And now, but that's this distinction between map and apply. Okay. Otherwise, it's the same example. Here's the implementation. So this is also 15 lines of code, but this cheats because this uses this helper in 3 lines that I didn't redeclare. Okay, so it's a little bit more complex. No. Okay, so we want to return a result after the wait all, and the result is this array of type. Well, the type is how to say it? You pass the lambdas, let's say, to it, right? And the lambda has a return type. This is type of the lambda, and this is exactly the type that you want to use for your sequence construction here. And so this is the additional complication in this case. Also, our worker proc now takes 2 input arrays, like the source and destination, and it does destination is OP of source. Okay. Reduce. Yeah, to explain what it does, if you don't know, it's easiest to explain as pseudocode. We start with the default value of t, right? This is array of t. And then we apply this OP on result. The best example is a sum, right? So if you would use plus here for the OP, you would get the sum. Yeah, and that's exactly what we're going to do. So plus equals for our numbers, and then this would be the resulting sum. And again, the implementation, now it's getting, yeah, it's still manageable. 20 lines, okay? But I think it doesn't, like here now you need to watch out that you, you need some, well, how to put it? You need some helper data structure to store the intermediate results, because eventually you want to do, because otherwise there's no parallelism involved. And you need to watch out here that you don't use an append to this sequence, because an append might reallocate the data in memory, which would be really problematic since we are running this in parallel. So you need to here to compute the final size precisely upfront before you can do that. But again, this is like Malebolgia gives you this power reduce. This is its implementation. Just use it. Don't worry about this. We got this one right, I'm sure. Fine. Yeah, I'm going to skip this one. OK, now it's getting so large that it doesn't even, it still fits, but all right. OK, so I'm going to skip these slides. So the point here is that the implementation is simple enough that I can show it completely in this talk, but I'm not going to do that. So let's see. OK, now more philosophy. So NIM is, like, think of Algol or Fortran. It's classic imperative style with a couple of functional programming elements and Lisp macro system. And I claim these additions that Malebolgia gives us are kind of the natural extensions for the language. Because what do you have? OK, you have function calls in NIM. You want to be able to say, yeah, this function call, run it somewhere else. So you need the spawn. Likewise, our function calls can have return values. So our spawn needs to support that in some way. This is this arrow. In sequential NIM, you have a divergent control flow in the form of case or if statements, which are structured like they can converge again eventually. And so we need the same way with the help of await all in our concurrent setting. And NIM doesn't shy away from mutability. So it has global variables that you can mutate, or you have these mutable parameters. And these are supported in Malebolgia via this locker of T idea. So, so the point is, this is like in some sense the minimal amount of 5 minutes, the minimal amount of features that you need to add to a sequential programming language to get concurrency. And in my opinion, these are much more elegant than, let's say, the actor model, right? This was the first attempt, was an actor model for NIM. It was a complete disaster. Later, I figured out that it's not just because I suck at this implementation, but I think the actor model has some fundamental flaws, and maybe we can, after this talk about that. Because in the actor model, you basically don't have return values unless you say, here in my task, this is the return, like call me back eventually later with this return. And this is very, very not functional programming then. Also, what I try to avoid here is channels for the same reason. So if you have a channel of data, in your source code, you have some block of code that does send to this channel, and somewhere else you receive from this channel. So you can easily make bugs like for instance, a very simple example, you create a channel, you store 3 values in the channel, and then you forget about it. And the type system would be happy, but your system is not correct. So, and this one here is, let's have a look again. Wait a second. Where is it? This one. No, this one. Again, you can treat all of these things as annotations, and the sequential algorithm is still visible directly, right? So wait all, I don't care. Just call fib directly, store the result in A, etc. And that's the elegance of this approach, in my opinion. And when you start to create something like this with channels, immediately it's not obvious anymore what actually was the algorithm that was tried, that we tried to implement. Okay, questions? Yeah.
How do you control the number of parallel processes that can occur?
Yeah, you simply specify at compile time. Like the assumption is you know the system it will run on. You know you have 8 cores. You simply tell Malebolgia at compile time, optimize it for 8 cores. Make sense? Okay.